When we gaze into the night sky, we see brilliance, stars, galaxies, nebulae, the visible tapestry of the cosmos. But what if everything we can see, touch, and measure makes up less than 5% of the universe? The rest, the vast majority, is made of something unseen. Mysterious forces that sculpt galaxies, shape space-time, and drive the universe to expand faster and faster. These are the invisible architects of existence: dark matter and dark energy. Before we get too deep into this topic, be sure to like this video and subscribe to the channel. This helps to bring more valuable content to the platform for your knowledge and understanding. Remember, knowledge is power. Now back to the episode. The story begins in the early 20th century, a time of scientific upheaval. Einstein's general theory of relativity, 1915, had just rewritten our understanding of gravity and spacetime. The universe was no longer static. It could bend, expand, or contract. Yet Einstein himself hesitated. To preserve a stable cosmos, he introduced a term into his equations: the cosmological constant, lambda, an invisible pressure preventing the universe from collapsing. Ironically, he would later call it his greatest blunder. But decades later, that blunder would become a cornerstone of modern cosmology, reborn as dark energy. In the 1930s, Swiss astronomer Fritz Zwicky observed something peculiar while studying the Coma cluster. A massive collection of galaxies. The galaxies within the cluster were moving too fast to be held together by the visible matter alone. By calculating their motion, Zwicky concluded that there must be something else, invisible mass, providing gravitational glue. He called it dunkle Materie, dark matter. At first, the idea was dismissed. The scientific world wasn't ready to believe in a hidden form of matter. But over the next few decades, the evidence would become impossible to ignore. In the 1970s, Vera Rubin, an American astronomer, mapped the rotation curves of galaxies, how fast stars orbited their galactic centers. According to Newtonian physics, stars on the outskirts should move more slowly than those near the core. But they didn't. Every star, no matter how far, moved at nearly the same speed, a cosmic clue that galaxies were surrounded by a massive halo of unseen matter. Dark matter doesn't emit, absorb, or reflect light. We can't see it directly. Yet its gravitational influence is everywhere. In how galaxies spin, in how light bends as it travels through the cosmos, and in the large-scale web-like structure of the universe itself. Through gravitational lensing, light from distant galaxies is distorted by invisible masses between us and them. These distortions allow astronomers to map dark matter indirectly, like tracing the outline of an invisible hand pressing against spacetime. Cosmological simulations, such as the Millennium simulation, reveal a universe woven together by filaments of dark matter, forming a vast cosmic web where galaxies cluster along invisible scaffolding. Scientists have proposed several candidates for dark matter, but none yet confirmed. One leading idea involves WIMPs, weakly interacting massive particles, hypothetical particles that rarely interact with ordinary matter. Another possibility is axions, ultralight particles predicted by certain extensions of quantum field theory. Others suspect sterile neutrinos, elusive cousins of known neutrinos that barely interact with the physical world. Around the world, physicists have built sensitive underground detectors, like the LUX-ZEPLIN experiment in South Dakota and Xenon-NT in Italy, in hopes of catching a rare glimpse of dark matter interacting with normal atoms. So far, the silence continues, deep, cosmic, and humbling. If dark matter holds the universe together, dark energy is tearing it apart. In 1998, two independent teams, the Supernova Cosmology Project led by Saul Perlmutter and the High-Z Supernova Search Team led by Brian Schmidt and Adam Rees, made a shocking discovery. By studying Type 1a supernovae, stellar explosions that act as standard candles for measuring cosmic distances, They found that distant galaxies weren't slowing down as expected. Instead, they were accelerating away from us. Some mysterious force, was pushing the fabric of space-time outward. This was dark energy, a term encompassing whatever is driving this acceleration. In 2011, Perlmutter, Schmidt, and Rees received the Nobel Prize in Physics for this discovery, a revelation that redefined our understanding of the cosmos. Today, the best cosmological models, like the lambda cold dark matter, lambda CDM model, describe the universe as being composed of roughly 5% ordinary matter, everything we can see, 27% dark matter, 68% dark energy. This means that most of the universe's content is still completely mysterious. Every atom, every star, every galaxy, everything we've ever observed is just the tip of an unfathomable iceberg. Physicists and astronomers are working across disciplines to understand these dark components. The Large Hadron Collider, LHC, at CERN continues to probe for new particles that might explain dark matter. Space-based observatories like Euclid, ESA, and the Nancy Grace Roman Space Telescope, NASA, are mapping billions of galaxies to measure cosmic expansion and dark energy's effects with unprecedented precision. Meanwhile, theorists are exploring exotic possibilities. Could dark energy be a property of space-time itself? Vacuum energy predicted by quantum field theory? Could dark matter consist of entire dark sectors, parallel particles and forces invisible to us but interacting through gravity? Or could our very understanding of gravity need revision, perhaps through modified Newtonian dynamics, MOND, or emergent gravity theories proposed by physicist Erik Verlinde? The more we uncover, the deeper the mystery becomes. What if dark matter isn't matter at all, but a sign that gravity behaves differently on galactic scales? What if dark energy isn't an external force, but a reflection of how time and space themselves evolve? New measurements from the James Webb Space Telescope and cosmic microwave background studies by Planck continue to challenge our assumptions, suggesting that the early universe may not align perfectly with our current models. The tension between local expansion rates, the Hubble constant, and those predicted by early universe observations hints that something profound, perhaps tied to dark energy, still eludes our equations. In the end, dark matter and dark energy remind us how little we truly know. They are the silent majority of existence, unseen, unfelt, yet shaping every atom, every orbit, every heartbeat in the cosmos. Our universe may be dominated by darkness, but within that darkness lies possibility, waiting to be illuminated. Perhaps the next generation of scientists, dreamers, and explorers will finally bring light to the unseen, revealing the true nature of the forces that hold and hurl the universe through eternity. If you found this content helpful, don't forget to like this video and subscribe to the channel. Leave me a comment. Let me know what you think about dark matter and dark energy, unknown forces of the universe. Join me next time for another deep dive into the mysteries of our cosmic universe.